with a little generic, just kind of a generic approach here. So I am going to rewrite this. We're going to try to develop a little bit this pattern that we're going to be looking at. So it says, now integrate both sides, or find the antiderivative of both sides. So I'm going to go antiderivative of the left side, antiderivative of the right side. So what's that antiderivative going to do with the d dx? How do they interact? Yeah, that's right. They cancel each other out. So I end up with f of g of x equals the antiderivative of f prime of g of x times g prime of x. And technically, I should have multiplied that dx over. So let me multiply that over now. Yeah, make that go away. Thank you. So then this is where this gets interesting, because if you think about it, all we did was we differentiated there at the start. And Marguerite said it really well, and everybody in here was like, yep, that makes sense, we're good. And then on the next step, we did the antiderivative of both sides. You're like, yep, the antiderivative is going to cancel out with the derivative, the differential there. And so we end up with this. We end up with f of g of x equals the antiderivative of f prime of g of x times g prime of x dx. And it's like, you look at this, and can you guys kind of see how this would cancel out with this? Because you're like, okay, antiderivative of a derivative, and maybe even say that it cancels out with that or something. But then when you look at this, something doesn't seem to fit, right? Because you would, if those things just canceled out, you would have this, and you would have this, and you got to admit there's like this extra factor just sort of hanging out there. Like, what happens to it? Where does it go? Let me just explain it to you with the boxes. The right side is basically this. The right side is the boxes all opened up and spread out and multiplied times each other. So can you all see, let me get rid of some of these extra marks. Can you guys see how this is kind of like the big box right here? And can you see how this is kind of like the medium-sized box, if you will? And can you see how Santa is like the dx? So what happens is, as you anti-differentiate this, you got to realize you're just undoing the chain rule. And so instead of things being unpackaged and multiplied, piece by piece, they're going to be put back in. So as Santa goes back in, bouncy Santa, there we go. Santa goes back in, essentially, like symbolically what that is, that's the dx simply going back inside and reintegrating with the x, because that's where it came from. And then this g prime, wouldn't it just be reintegrated back into the biggest box? And so this just goes back into here. And so what people will look at, they'll say, let me just write this again, just with all the extra marks. They will say, they'll say, hey, I get it. I get that this antiderivative is going to cancel out that prime, and maybe even cancel out that prime. But where did this go? If you look at the left side, doesn't it seem like that extra factor of g prime or g or whatever just like disappeared? You see how it just seems to have like just gone away? The answer to the question of where did it go is it just went back inside. It just went back into the bigger box. Because all we're doing is we're just reversing the chain rule. If you ever question where did it go, ask yourself the other question, where did it come from? Didn't it come from a result of doing a derivative of the inside? So if you're going to undo that, it would just be put back into the inside where it came from. Does that make sense? Okay. So I would encourage you guys to learn to recognize the pattern that we just saw up there. Here it is, related to again. I think there's a couple of different ways that this is presented, but it's all basically the same thing. Yep, more of that, more of that. We'll talk about change of variables in a little bit. It is going to be most beneficial for us to do. So if you guys would, please take a look at number 1. I'm going to help you with this. I'm going to show you, this is where you're going to learn about Timmy. I'll show you a way to recognize the pattern. Okay, so pattern recognition can be challenging, right? Pattern recognition can be very, very challenging, so I want to point out the important things to recognize. First of all, This could be done, this particular question could definitely be done without any of the stuff I'm about to show you, but it would be highly impractical. You know what you could do? Any suggestions on what you could do to completely avoid all this new stuff? You could completely, it wouldn't even be FOIL a bunch of times, right? You could multiply x squared plus 1 times itself 100 times.
So did you purposely put numbers in?
I purposefully made the 100 a fairly large exponent, right? Because there is a way you could do this. It's just not practical time-wise, right? Like the honest truth is if I just set you onto this, I'm like, all right, guys, start multiplying. You know, if you took me up on that, I think I would come back in like 2 hours and you'd maybe be halfway done. I'd come back tonight around, like 9 p.m. and you'd maybe be done. I mean, it would take you forever, right? Maybe not that long, but it'd be close. It would take you a long, long time. And even then, wouldn't there still be that nagging thought in the back of your mind like, oh, did I add it all up right? Did I really multiply? Does it really? Yeah. Like, it would be...
when I do that, it's like to the fourth, I'm like, I forget if I did it 3 or 4 times already.
Wouldn't that be the type of thing that would be better left to a computer?
Yes.
Yeah, so we're not going to do anything like that. So here's what you got to recognize. A couple things here, guys. If I were you, I'd make notes of this. First of all, please recognize that overall, your integrand is a product. That is crucial. To this point, we have not really done anything with products. Other than when we see a product, we do whatever we got to do to make it not a product, right? So up to this point, we have avoided products like crazy. The other thing you got to notice here, one of the other things is, one of your two factors, namely this one right here, is composite. Okay, so you've got a product, you got a function times another function, and one of the two, maybe even both of them, but at least one of the two is composite. That's really, really important. So does that pattern make sense? Like, do you see how you could identify those things? Okay, so it's got to be a product. One of the two factors at least, maybe both, have to be a composite.
What does it mean to be a composite?
Composite means that you've got a function, like a non-trivial function, inside another function.
Okay, so there's like... Okay.
So I would say that like x to the 5th is not a composite. I mean, you could sort of call it that, and we've kind of done that before, but I would say that it's trivial in the sense that the input is just an x. But I would say that cosine of x to the 5th, we would call that a composite for sure because the input is not just an x, it's a cosine of x. So kind of like this, x to the 100th, I would say that's not really composite. I don't think I would think about it like that. But I would say x squared plus 1 to the 100th. Well, now the input's not just an x, it's x squared plus 100. To me, clearly a composite. Okay. Okay. So far, so good? Okay, so I'm going to show you a couple ways to do that. I think I will. I'll probably show you a couple ways to do this one. We'll see. So can I be very unteacher-like and show you the quick way first? Because I'm really hoping that you'll latch onto this, and for some of these easier ones, you'll just do it the quick way. For some of the tougher ones, you're definitely going to want to do it the other way. But for these, the quick way is great. So here's what you do. You recognize product and composite. Is that good? So I'm going to erase those so I can work with this a little bit. Here's how you do this. We're going to introduce this character named Timmy, and here's how he works within this. We're going to carefully look at the inside. We've identified that left factor as composite, right? So we're going to carefully look at the inside, and we're going to compare that inside to the other factor. And we're going to ask ourselves a question: has the chain rule been done correctly? In other words, did Timmy mess up the chain rule? So is the derivative of the inside that other factor? What's the answer, yes or no? So this is the rarest of occasions Timmy didn't mess up. He almost always messes up. He has a real problem with the chain rule, basically. He didn't mess this up. And here, so Jane?
Would you mean like we have to check the problem?
You have to check to see if he messed up. So here's all you're doing, Jane. You're looking at this and you're asking yourself, like you're identifying the inside.
Yeah.
And you're saying, okay, the inside, like here's what's going on inside your brain. The inside is x squared plus 1.
Right.
What is the derivative of the inside?
2x.
2x. So does that match the other factor?
Yes.
That's an A. And if the answer is yes, That means that Timmy did not mess up the chain rule, and this is actually going to progress quite easily. So that's what should be going on in your head. Does that make sense? So then we looked at this and we said, you know what? Timmy, for once, didn't mess up the chain rule. The chain rule has been exactly executed, and so all we have to do is reverse the chain rule, and here's how we do it. We simply anti-differentiate the outside function. So would you guys agree with me that the outside function, like the big box, is to the 100th? So the way that we anti-differentiate that is we say x squared plus 1 to the 101 divided by 101. And then we put plus c. And we're done. So then this is where somebody, I think, would have a really intelligent question. They'd be like, well, okay, I totally get the whole 101 thing, but where the heck did the 2x go? It just went back inside. Okay, can I show you by checking this what happened to it? Check this out. What would be the way, like if you were unsure of yourself, what would be a way to check your answer to see if it really is the antiderivative? Do the derivative. Yeah, that's right. So if we did d dx of our result, here's what would happen. We'd say, well, first of all, the derivative of plus c is just 0, right? We'll just, do that right away. But then wouldn't we just do a power rule here? Like a power rule with a chain rule? So the 101 would come down in front, and we would subtract 1 from the old exponent, and we'd get 100. But then wouldn't we have to multiply by the derivative of the inside? So the derivative of the inside is 2x. Of course, this cancels to just be a 1. And maybe this, by looking at the check here, maybe you can see where the 2x actually came from. Didn't it come from just a result of doing a chain rule derivative? So in reversing that, wouldn't it just be reintegrated back into the inside? So it's not really disappearing. I mean, you can hear it in there, right? You just can't see it because it's back in as part of the input. Does that make sense? Okay. Question is now, what if Timmy messed up? Let's take a look at that. So please take a look at number 2. Timmy, come on.
Right?
Terrible Timmy.
Timmy has been around for like 20 years. Like I invented Timmy like in my second year of teaching calculus. And I don't know where we came up with that.
After like a student.
All of the years, actually not. For all of the years that I've ever taught this, there have only been 2 people named Tim. There is actually one this year, but there was one like 5 or 6 years ago, and there's one like 12 years ago or something like that. So I always have to say, no offense intended. This is just a fictitious character, not directed at you. He's been around for a long time. So anyways, there's nobody. I don't know, like when I thought of like someone that like would, that's just the name that came to my mind. Come on, Timmy, can do better.
Because Mr. Blake has Jack Sparrow, and you've got.
Oh really? So he has his own fictitious
He has his
character?
own. Well, it's not like fictitious.
Yeah, we know the pirates thing.
It's
Yeah.
just-
So Timmy is even more bland. He's just like, you don't even know who he is, right? You can't even picture him. Oh, be nice. Okay, so guys, do this one. I want you to do this one with me. Then I'm going to set you guys off and see if you can do a few of these on your own. So number 2. Again, it's going to be really tempting to just think to yourself, hey, this is in section 4.5, so these will all just kind of follow the same kind of cadence and pattern and everything. It's really important that we notice the pattern. So let's look at this again. This is a little bit less obvious, but please notice that this integrand is a product, right? It's cosine of 5x times dx. And the more important thing to notice here is that one of your factors is composite. That's the key piece here. In fact, cosine 5x, well, it's not exactly like that, but can you see how it's the 5x is the input for cosine? That makes sense as far as the composite piece?
Why
Yeah.
is it important that it's a product?
Why is it important that it's a product? Because the result of the chain rule always multiplies the derivative of the inside times the previous step. So it's going to be something times something overall for the chain rule reversal to make sense. No. Remember, chain rule is the derivative of the outside with the inside still in there times.
Well, wouldn't always your product is always like the
Yeah, and that's why I say the more important piece here is the fact that the one factor on the left is composite. In this one, that's the more important thing. But then when you look at number 3, can you see how we're kind of back to the same sort of thing we did with number 1? It's still it's a more of an obvious product. You're right; they're all products, but the fact that this number 2 has a composite piece. Like, let me just give you a comparison. What if you had this? You could look at that and you could say, "Hey, that's a product too." It's got to be a product where one of the factors is composite. That pattern doesn't fit here, right? Okay. Oh, so number 2, it's a product. You see the composite piece. And so what we would do here is we'd recognize that, and we would say, all right, did Timmy mess this up? So let's ask ourselves, what's the inside function? What's the inside of the composite? 5x is the inside. So we're going to ask ourselves the next question, what's the derivative of that inside? Is 5 the other factor? Oh, Timmy messed it up. So here's what we do. I'm gonna rewrite this just so I have room. Here's all we have to do, and I hope that this makes sense to you. If Timmy messes up, which he totally did, all we have to do is fix it. So the other factor was supposed to be a 5, wasn't it?
So would the coefficient just start as like 1?
We'll get there in a second. Yeah, I think you're starting to see a good pattern here. I'm going to fix his issue. He should have had 5 cosine 5x, right? But of course, you all know, like, your little like math sense is saying, well, hey, you can't just like change it, turn it into a 5 when it used to just be a 1. You can't do that. Sure I can, as long as I also balance it out on the outside.
Oh my God.
What did I want you to think about this for a second. What did I really just do? Nothing. I multiplied by 1. No, seriously. As far as changing the value of this, what did I do? I didn't do anything. I multiplied it by 1. I can imagine how insulted you'd be if I was your boss and I was like, hey, I want to give you a raise. I'm going to give you a 4% raise for this next year. And you're like, I'm insulted. And I'm like, okay. We'll take that 4% and we'll multiply it by 1. I didn't do anything, right? It's still 4%. And so if you look at what I just did there, I multiplied by 5/5, didn't I? I didn't change the value of anything, and that's actually a good thing because I can't just change the value of it and call it the same thing. What I did is I multiplied by like a smart one. I multiplied by 5/5. Why is that so smart? Well, the reason that it's so smart is because this now perfectly fits the chain rule. I have fixed Timmy's issue, so here's how this would proceed. The 1/5 doesn't go anywhere. It's on the outside of the integrand. But where does the 5 go when I actually find my antiderivative? Back inside. It goes back in the bigger box.
Can you add it later?
What do you mean by add it?
Like, could you just do the antiderivative and then put the coefficient of whatever you needed to?
You mean the 1/5?
Yeah.
There's a variety of ways you can get there. Make sure that what you're doing actually is readable and makes sense. So in case you mess up, I can look at it and be like, oh, I see what she did, instead of just like this, bing, this magical answer. Certainly don't want that. Okay, so then what's the antiderivative of cosine, right? We're just antidifferentiating the outside function. It's sine. So it would be 1/5 sine of 5x plus c. And once again, if you ever have any doubts about the accuracy of your answer here, your antiderivative, all you got to do is do a derivative and check to see if the result matches the original integrand. So let me say this at this point. Some of you right now might be saying, oh man, like, I don't know if I'm like flowing too well with this whole Timmy messed up the chain rule pattern recognition thing. I would like it better if you just gave me step 1, 2, 3, 4, 5. If you're thinking that, I think on this next one, number 3, I'll show you both ways. Because if you just do step 1, 2, 3, 4, 5, whatever, should be in good shape. There is a method like that. And I'll show that to you too, okay? So if you guys would, please try number 3. See if you can use the whole Timmy messed up the chain rule pattern strategy with number 3. And then I'll kind of go through that, and then I'll show you the other way too for number 3. Maybe just automatically did you guys automatically just say that this is really x cubed plus 1 to the 1/2? you definitely want to do that. Just for numerically speaking, it makes it a lot easier. Okay, so like I said, I'm going to show you both ways here. On the left, I'm going to show you the Timmy messed up the chain rule pattern, and then I'll show you the other way here in just a second. So the first thing to notice, of course, is that you've got a product, and importantly, one of the two factors is composite. So did you guys notice that this over here was the inside of the composite?
Yes.
So if you're going to use the Timmy messed up the chain rule pattern, honestly, it's a shortcut. A lot of what you do is just up here. Here's what you would be thinking. What's the inside function? X cubed plus 1. And what's the derivative of that?
3x squared.
Is that the other factor? It is not. So what does that mean? Timmy messed it up. We can fix it though, right? The other factor was supposed to be 3x squared. He just wrote x squared. How do we fix that?
3.
Multiply by 3. So I'm going to go times 3. So now we have a perfect chain rule pattern. Timmy, we fixed it for you, but we've got to also make an adjustment to compensate for what we just did, and that's to multiply the outside by the reciprocal of what we just multiplied the inside by, right? Multiply the inside by 3, the outside by 1/3. When you do that, the 1/3 does not disappear. It continues on down, and then as we do our antiderivative, the only thing that you actually have to do an antiderivative of is your outside function, which is 1/2, and it would end up looking something like this. X cubed plus 1 to the 3/2 divided by 3/2. Are you guys okay if I just write times 2/3? Right, because dividing by 3/2, multiplying by 2/3, same thing. And then don't forget your plus c. So you end up with 2/9 times x cubed plus 1 to the 3/2 plus c. And again, if you have any doubts, just differentiate it, do a chain rule, and see if it works. So I'm going to contrast this with this other method. So can I show you steps 1, 2, 3, 4, 5 here? So here's a very structured way that's way less of a shortcut. Okay, so we're going to start off with the exact same expression, and here's what we do. And this is called substitution. That's what this method is called. So this is not a shortcut. This is a very step-by-step method. So step number 1. What you're going to want to do is you're going to want to set up your substitution. So this is an alternative. You don't have to do it this way. Later on, there are going to be some questions where you're going to want to use this. We'll develop that a little bit more probably next time on Wednesday. So here we go. We're going to set up our substitution. We usually use the letter U. So sometimes you'll see this written as U substitution, but it's just substitution. The way we're going to set this up is we want U to equal the inside function. So what's the inside function? That's right. And then what we're going to do, we're always going to do our differential. And so our differential here would be du equals 3x squared dx. Do a derivative and just multiply the dx over. And once you've set this up, we're going to start trying to substitute. So, would you guys be okay with this? Instead of the square root of x cubed plus 1, I'm going to substitute and call it the square root of u. Does that make sense based on how we set that up?
Yes.
But then I've got to be honest about it and say that I still have a 3x squared, and I still have a dx. Who is it? Jeopardy Unit 3 test. There we go. Is try to substitute the rest of this, and here's how this would work. I'm going to take this, and I'm going to solve for dx. So it's going to be du over 3x squared equals dx. I'm just dividing both sides by 3x squared. And this is actually, oh shoot. Sorry. I made a little, I made a little typo. This should just be x squared, right? Sorry. Do you see, I just got over enthusiastic. I just wrote 3x squared a second ago, and I just kept on writing a 3, right?
Oh.
So it's just x squared root u times dx. Okay. So then I can complete my substitution by doing this. I'm going to replace the dx with du over 3x squared. Why is this so great? Wouldn't the x squareds just cancel out? And I'd end up with something like 1/3 u to the 1/2 du. And now we have a pretty simple antiderivative to do. I'll just use the power. Sorry?
Never mind.
Okay.
So du is equal to 3x squared dx.
3x du is equal to 3x squared dx.
If
And
you put...
so I just solve for
I guess you wouldn't
dx.
substitute twice, but like, because 3x squared dx over 3 would just be...
You could substitute in 2 steps if you wanted to, or the 1 step. Yeah.
Wait, where'd the 1/3 come from?
So it's the du over 3. Right, so the x squareds canceled out. Du over 3 is the same thing as 1/3 times du. Does that make sense?
Not really. Sorry.
Okay. So
I was confused how you got 1 from you.
I didn't get 1 from du. The du is still in there. What I'm saying is that du over 3, and you see that in there, right? The du over 3 is the exact same thing
Oh,
as 1/3 times du.
gotcha.
Okay. And then I just moved it out to the front. I just changed the order on it. Okay, so this will come together. This will actually come together right now. So my antiderivative is going to be 1/3 times u to the 3/2 divided by 3/2 plus c, but it's really times, so it's copy dot flop. So it's going to be 1/3 times 2/3 u to the 3/2 plus c. So it's 2/9. My final step would be to plug the whatever the u actually is back in. So it was x cubed plus 1 to the 3/2 plus c. And of course you can see that that and that are the same. You can also see that in this particular instance, the substitution took a lot longer stepwise than did the Timmy messed up the chain rule pattern thing. But that doesn't really matter that much, right? You want to be correct about it. I like the Timmy messed up the chain rule pattern on a simple one like this because you can do it fast. You go times 3, times 1/3, antiderivative, and you're done. You do the substitution, that'll work too. It just takes a longer time. Yeah.
Will there be problems where like substitution doesn't work and problems where Timmy's rule doesn't work? Like I know there'll be ones where it's better, but like are there any problems that either of them don't apply to?
Well, in the grand scheme of things, in all of calculus, absolutely.
Well, in there.
In this course, substitution will always work. Timmy will mostly work.
Okay. Will you
90,
tell us how to like
98% of the time.
differentiate?
You'll see an example or two where you try Timmy's pattern thing and you're like, oh, it didn't work. Go to USub. Yeah. Okay, so I want to give you guys again just some free reign to try another one here. So if you guys would please try number 4 and use whatever method you want. In my opinion, number 4 is definitely one where I would use Timmy messed up the chain rule. I wouldn't mess with substitution at all for number 4. But you get a pick. So you pick whichever one you think works better for you and do that one. Ready to go.
U minus. The opposite of the will be add, and it's n plus 1.
What do you guys think of Timmy on this one? Does that seem to work okay? Hope it did. Okay. So you hopefully recognize you got a product and one of the factors is composite and you identified the inside as x squared plus 1. Here's the big question. What's the derivative of the inside? And is the other factor 2x? So Timmy messed up again, but he didn't mess up that bad. What number do we need to multiply by to fix his issue? And you got to multiply by 2. So I'm going to multiply by 2 on the inside. That means I've got to multiply by 1/2 on the outside. And now we can do our antiderivative and say that the 1/2 remains there. We get x squared plus 1 to the 10th over 10 plus c. And of course, the 2x just went back inside as part of the input. So for a final answer here, maybe 1/20 times x squared plus 1 to the 10th plus c. What do you guys think? Good? Peeking over shoulders, I saw a lot of that. Okay, cool. Let's get a little more practice here. Take a look at number 5. I want to help you set this up. Yeah, so you notice it's really not a product, is it?
You can make it.
But you can make it one, right, by moving up. So I would do that first. I would say this is the antiderivative of x squared times 4 plus x cubed all to the what power?
Negative.
-5. There you go. Dx. Okay, so see if you can proceed from there. Decide if it's Timmy messed up the chain rule pattern, or if you want to do the substitution route, you can. Whichever way you choose, try to execute that. By the antiderivative.
So we use either one where it's
Yeah, nothing really works there. That one's an awful mess. So this one, Timmy's pattern doesn't work. That one for sure doesn't. Timmy's pattern works here okay, but it's a little bit much, right? It's a lot to see. Those are the two where I'd be like, you really got to use
On
substitution there.
something like this, would you get to like pick which is your function?
You can pick, and it'll be fine either way, which is a really curious result, but it will work either way.
Track my signs. Just.
Right, Brendan, how's it going?
I don't care.
You cured Timmy of his issues yet? Okay, good.
Okay.
All right, have you guys all compared answers and stuff? I think you should. It's always good thing to do. Get it? Has Timmy been fixed yet?
Timmy has been fixed.
All right. The bad news is he's going to mess up again tomorrow.
How do you do
And the next
multiple composites, like multiple products?
Oh, like with well, so look, there's one with cosine 4x, sine 4x coming up in a couple of, maybe one more. Yes, are you talking about something like that? Or that's 3x, I guess. We'll use substitution for that one. You could use the Timmy messed up the chain rule pattern, but we'll use substitution there. Okay, let's see how we did with number 5. Andy, how bad did Timmy mess up on number 5?
That's a factor of 3.
He did mess up by a factor of 3. So did you guys fix his issue like that? And then, of course, you make our adjustment for that by multiplying the outside by 1/3. The 1/3 continues on. And as you do your antiderivative, the 3x squared just goes back inside as part of your input. And then we need to do our antiderivative. It would be 4 plus x cubed to the -4th over -4 plus c. So if we clean this one up a little bit, it would maybe be -1/12 times 4 plus x cubed to the -4th plus c. What do you guys think? Okay, cool. Move on to number 6. I like number 6, I think. I really like number 6.
Yellow seems scary.
Actually, you know what? Before we do number 6, let's just briefly talk about number 7, and then I'll have you guys finish number 6. So with number 7, do you guys see how if you asked the question about Timmy, you said, hey, what's the inside? What would you say? Well, the inside is x squared, but the derivative is 2x. And you'd ask yourself, is the other factor 2x? And you'd have to say no. If you ever find yourself doing this, saying, all right, well, I can fix this. I can fix this by just saying, if I multiply the inside by 2x and the outside by 1 over 2x, what that means is it's not this. It's the wrong form. You cannot adjust by a variable like an x. You can only adjust by a constant multiple. So if your process leads you to multiply the inside by 10 and the outside by 1/10, you're good. But if you're like, okay, in order to make this work, I got to multiply by x squared and divide by x squared, you got an issue. You have the form wrong. You need to simplify it. There's just something wrong with that that you need to investigate a little bit further. That simply won't work. Does that make sense? Okay, cool. All right, so number 6 then, the antiderivative of sine of x times cosine of x. Clearly a product. The composite piece is a little harder to see. Right? So I'll give you a couple minutes to try to think this one through.
I think I should just.
Why don't we track one though? Like,
Which one are you looking at? Are you on the right? But you're looking at this as your answer?
No, but like especially if I start, and maybe, I don't know.
So do this, do it like this. I think that that is a reasonable proposal for an answer. Differentiate it. Compare your derivative to the original. That might lead you to understand what you need to do. Possibly. Yeah. You've kind of made a mistake, but it's an understandable one that you can fix pretty simply.
Just the neck.
Right out, actually do derivative and see what you got.
I got it right here. Yep, just like it. Same answer. One over C. It's a trick, it doesn't work.
Yeah,
This defies math.
the trick does kind of work here. It does work. You gotta see a little bit differently. Just so you guys know, we're in good shape here. When I see you guys on Wednesday, we'll continue to work with these same types of things. We'll advance it a little bit, and I think we should be in pretty good shape to finish up on Wednesday, which means that Thursday should be a nice day to review for you to ask questions on web assigns or whatever you've been studying, leaving us with Friday for our quest. And that quest on Friday, kind of like your loop quiz, can go either way. It can be a quiz or a test, whichever is nicer to you.
Did you like test both sides?
Yeah, it's very unsophisticated. I like plug it in, look at the grade. All right, erase it. Plug it in, look at the grade. Oh, we're going with that one. It's not very complicated. It's scientific, just not very elegant. I can't think of a better way, so that's what I do. Just enter it. Yeah, I like that one better. I'll go with that one. All right, so I think it's about that time. Obviously a product, right? Composite, not so obvious. Here's what you can do. You can look at either one of these as being the inside. I am going to choose, you could go either way. I'm going to choose this to be my inside. I'm just going to put parentheses around it, and I'm going to put to the first. So similar to what we've done, I haven't changed a thing. I've just changed the form of it to help me see something a little bit better. So if I write it like that and I say, what's the outside? I would say to the first. What's the inside? Sine of x. What's the derivative of that inside? No, the derivative is actually positive cosine. So when we think about Timmy and him messing up, on this one, if I set it up this way, I'd say, did Timmy mess up? And the answer is, nope, he totally didn't. The derivative of the inside is the other factor. So what I do here is I just anti-differentiate the to the first power. So don't I just add 1 and divide by the new exponent? So check this out. It would be sine of x, quantity squared, over 2 plus c. Or you could put 1/2 sine squared of x plus c. Same thing. Okay? The question is, of course you can differentiate that and you can see that the chain rule makes it work out really nicely. The question is, what if I did this a little bit differently? What if I said, you know what? Instead of sine of x being my inside, what if I chose the other way? See how this would work out. So let's think that through. So if I did that instead, I would say Timmy messed up this time. He messed up by what factor? -1. That's right. So negative would go here, a negative would go there. This negative continues on, whereas this just goes back in as part of your input, right? And then I would go cosine of x squared over 2 plus c. So I get this -1/2 cosine squared of x plus c. So then you got to stop and think to yourself, whoa, wait a minute. Those two had better be equivalent, and they are. Because what?
They're opposite of each other. More.
There's a deeper reason. It has to do with the Pythagorean identities. It's 3 o'clock. I don't really have time to show you. Unless you want to stick around. If anybody wants to stick around, I'll show you. So check this out. Couldn't I replace cosine squared with 1 minus sine squared? Right? So it gets better. So you get negative 1/2 plus 1/2 sine squared of x plus c. So then you look at this and you say, well, this looks a lot like this, but what about this? What's that? It's part of the constant, right? What's negative 1/2 plus c? Some other c, right? It just gets folded into the constant. So they really are the same thing. All right, see you guys. Great job today. Awesome. Good participation.
See what I wrote on your
Actually, it was very.
I am not going to
Thank you. See you later.
be here at the end of the day on Friday,
Okay.
and so that's our quiz, right?
Yep.
So I was going to ask if I could take it. Oh, you have I didn't mean it. It was one letter.
Yes and no.
You'll find it. I don't want it.
Go find it somewhere.
So the only, so you saw the, yeah.
You'll laugh at it.
Mr. Anderson.
I promise.
So the only issue is
It's
the
not
selfish
like
one,
bad.
you
It's
feel
not
like
like
something.
inappropriate.
Okay.
And I've got a gray class and a red class, and so like business stuff is the only time. Other than that, it's fine.
Okay. Do you think
So,
there'd be another teacher maybe in the corner that could like,
at least start it.
yeah, watch
Like, all they need to do is
Take
like
it
walk
until
down there and get some food and walk back up, so it's not gonna take that long. Do you have a teacher, by Eden?
Eden,
A teacher that you know? that
push
you
in your
can-
chair.
I could ask Mr. Cat, because I have a track.
Just be nice to him because of his hip. Let's make life as easy as possible on him.
I forgot about that.
Thank you, Ian. Have a great day.
I know Mr. Pettis.
Maybe send them an email and just let them know kind of what you're thinking. It would be like 10 minutes. It's
Yeah.
not like they'd be there for a whole hour or anything.
Okay.
Otherwise, it's fine.
Okay,
Thanks for letting me know.
Thank you.
Yep.